All right, so now we're gonna move to the third question. Now, in this third question, we're gonna look at the responses and we're gonna look at the roots of our characteristic equation from, remember, if we have a transfer function just like this will be our transfer function, and we are looking at the second order transfer function. We have k over tau squared s squared plus 2 um, tau dampening factor multiplied by s plus 1. So here we are looking at the second order transfer function. Like I said, this bottom part, this denominator, represent the characteristic equation, right? So when you have a characteristic equation, you can equate it to 0, which is our foreseen function to be 0. And then we determine the roots of this quadratic expression, which will lead to give quadratic equation the moment we equate it to 0. Now, after determining the roots of this, it's a matter of whether the roots are real or the roots are complex. Okay, so when you have the complex roots, we should be able to know how to represent those roots and talk about the stability of those roots. And then referring to the roots, we can use the Bibo technique to determine the stability of our response, whether it is bounded, again, we determine the bounds of the response, whether it is bounded input, we say Bibo. It's a bounded input, bounded output. Okay, we will decide from there. So what's happening here is you should be able to know your transfer functions, not your transfer function. You should be able to know your roots. Say maybe, okay, it's fine. Let's perform through this. Now let us try to answer question number A. So they say determine whether the following second order poles lead as squared. This is the second order, by the way. Determine whether the following second order poles lead to a stable system. Illustrate using rough sketch of poles response. So to answer question number A, this is gonna be, we have number A, right? First thing first, you need to determine the poles of that question. Like I said, this s squared minus 4s plus 12 is actually coming out of the denominator of your transfer function, of which we're going to equate that to 0 and solve the roots. Okay? So here we are looking at the poles, and then here we are looking at the zeros. So now, to determine the roots, it's either you complete the square or you use your quadratic equation. So most of the time I prefer to complete the square. S squared minus 4s. Actually, here it's supposed to be positive, by the way. Okay? Here it's supposed to be positive. 4s plus 12. So now let us complete the square. Okay? When we complete the square to this equation over here, assume that it is equated to 0. When you complete the square over here, we have s squared plus 4s. What is the half of 4? It's 2 squared. It's going to be 4. Is equals to, I'm going to take this 12 on the other side of the equation. It's going to be negative 12. And then I add the very same thing over there. And then here I'm going to have s plus 2 to the power of 2. And then this side, it's going to be negative 12 plus 4. Why am I struggling to do that with my head? It's negative 8. We have negative 8 this side. And therefore, remember, this is the negative answer. When I put the root sign under it, it's going to be imaginary. It's going to be non-real, but it will lead to a complex number. So that means when I take root sign on both sides, the side I'm going to have s plus 2, which will be equated to, this is going to be, when I put root sign, right, it's going to be root of negative 1, root of 8. So root of negative 1 will be my complex. I'll write I, I'll write J. And therefore, I have root of 8. And then remember, when you put, okay, let me do it like this so that mathematically, negative 8 here. When you introduce sign on both sides, you put plus or minus over there, okay? So we're going to have plus or minus j root of now positive 8, which is negative root of negative 1 is going to be j. And therefore, what is root of 8 is 2 root 2. So here we're going to have, I'm going to transpose this 2 to the side. It's going to be negative 2. We have plus or minus. What is root of 8? J 2 root 2. And therefore, we have 2s here. The first s is going to be a negative 2 plus j 2 root 2. And the second s, which is s2, it's going to be negative 2 negative j 2 root 2. So we can see that our roots are in a complex form. We have a complex number, and then when you have a complex number, you're supposed to understand that we have the real part, and because we have j there, we have the imaginary part. This is the real part, and this is the imaginary part, okay? So what we do here is we're going to plot these two rows onto a Cartesian plane. So we have our roots like so. This is our Cartesian plane. And then on our Cartesian plane, we have the imaginary part over here. And then here we're going to have our real parts. Okay, on the x-axis, y-axis is our imaginary parts. So now let us plot these two roots onto here. We have negative 2, which is real. And then our imaginary part is positive 2 root of 2, right? So I'll assume that 2 root of 2 is here, which is imaginary as j. And therefore, this one, which is negative 2 root of 2, it's going to be here. And then negative 2 will be here. And this also has negative 2. So, oh, I'm lying. Here's the coordinate, and then here's the coordinate. So let me erase that x over there. Now here's the coordinate, and then here's another coordinate over here. See, these are the coordinates for this Cartesian plane. So now after drawing the coordinate of this Cartesian plane, note this, when your real part or when your points are on the negative side of your Cartesian plane, we have a stable system all the times. Okay, we have the stable response all the times. So meaning rough sketch illustrating the pole responses. So now here we're going to draw our response over here on how it's going to actually look like. So now to draw this response, I'm saying to you, we have a stable one. So something that is stable will always approach, but something that is unstable will always move away, maybe to infinity. It will move to infinity, but when something is stable, it approaches some certain numerical value because it is stable. You understand? So I'm saying to you, in this case, because we have the negative side, we have the stability. But how are we going to represent the stability at this point in time? Now, the stability is we are approaching the set point. So meaning this is what we're going to have, okay? So here it will be our function, which is the response from the transfer function, the inverse of Laplace. I'm going to get this, and therefore this will be t. And therefore, this is how our function will actually look like. We are approaching the set point. You understand? It is settling at this point in time because we are actually approaching the set point. And therefore, now here we are talking about a stable system, and we are also talking about what? Referring to Bibo. We are talking about the We are looking at the area under the curve, okay? We say it is bounded, it is definite, okay? So we say it is the bounded output, because here we are referring to the output. So because the response, we have the bounded output. By the way, Bibo, it is satisfied because our system, it is stable. But if the system most definitely it is not stable, the Bibo won't be satisfied. So that's how we solve number A. And then how do we solve number B? To solve number B, we have s squared minus 9. Once more again, complete the square over here. How are we going to complete the square? We have s, okay, this one you don't even have to complete the square. We can just factorize it. Let's just equate the equation to 0, because again, we are talking about what? We are talking about the characteristic equation, and so we equate this to 0. So here we're gonna have s minus 3, s plus 3 is equals to 0. So our S1 will be negative 3, and our S2 will most definitely be positive 3. Right? This is our roots. And then we draw our Cartesian plane. Remember, here we have the imaginary part, and then here we have the real part. So imaginary part is 0, and then our real part in this case, we have negative 3 and positive 3. So negative 3 will be here, positive 3, I will assume that it will be here. So we have a point over here, we have another point over there. Now have a look at this. What's happening is it feels like it's in between the stability and instability, because I said to you, when we have the negative values this side, we say it is stable. But the moment we have the positive values on this side, it is now unstable. Okay? So now when it is unstable, I said to you, when it is stable, like this, it is stable, it approaches something, meaning it approaches the set point. So here, we can't have something that is partially stable and unstable. In this case, you're going to take it that it is unstable. You understand? So when we draw the response to this, y, and therefore here we're going to have t. When we draw a response to this is unstable. And then how it is unstable is it will start as if it is stable, and therefore it will move away from the stability. So here we're going to have exponential function. If you want to understand how to go about for this, by the way, you can also use this equation and determine the inverse transform. You will see you're going to have e to the power of b, blah, blah, blah. So the fact that you have e to the power of something, this will tell you that you're going to have an exponential function. But here, because it's just a number that looks like this, you're going to have the sinusoid, you're going to have sine functions when you perform the inverse Laplace. It's just complex, but you can also look at it like that so that you understand what type of response you're going to draw. Am I going to draw the exponential function, the sinusoid, the linear function? The linear function, to draw the linear function is when we have the ramp. Maybe we have something like, let me see, s squared, 1 over s squared. The Laplace of this, it's going to be straight line, right? Which is going to give us a ramp. And then when you have 1 over s Laplace, the inverse of Laplace, not the inverse of Laplace here is going to be a constant, meaning you're going to have a straight line throughout, which is like step in what step up, it's just what step up input, right? Yeah, it's not a ramp input. All right, so let's say where's my pen now? All right, there it is. Cool. So let's draw the response then. So here, the response looks like it is a little bit stable. It approaches something. And we're going to draw exponential function, by the way, for this one. So now, this exponential function, it won't go, and by the way, it's going to be, it won't go like this. Let me show you. It won't go like this. You won't start like this, and go like this. It won't approach, because the moment if it approaches this, now we are talking about the stability. But here, this thing, it is not stable at all. So it's supposed to be away from this asymptote, which is 0. So that means, to the white pen, that means it's gonna move like this, and it goes up just like so, to show that it is running away from the asymptote, meaning it's just going to infinity. We don't know where it's going because it is unstable. Something, when it is unstable, it is irrational, right? So here we have what type of response. It is unstable and it doesn't satisfy people. So we have unstable, right, response. And at the very same time, this is unbounded output. That output, right? And therefore, yeah, that's how we go about for this one over here. And then now let's have a look at this one, which is number C. By the way, I will leave number C and number C to you. You're just gonna repeat the same thing over and over again. An overview, let me tell you, okay? If for number C, basically when you complete the square, you're gonna get something that looks like this. Ne? You're gonna have your roots probably looking like this. You're gonna have the roots here. You're also gonna have another root over here. It's on the negative side, right? So when it is on the negative side, what does that mean? That means it is stable, right? So we are approaching something. You understand? So look at this one and look at that one. So again, having a look at this function over here, because it is stable, the roots will be the same, the numbers. So you can also refer to your Laplace transform so that you can see what type of function you are actually going to draw. So in this case, the type of function that we're going to draw is going to be exponential, okay? It's going to be exponential. So the response for this actually going to look like this. So we need, it doesn't start like this. It immediately goes down, okay? Immediately goes down just like this, to show that and you can start, but yeah, it won't be easy for you to just, it's fine. You can start it like this. It immediately it goes down to approach something over there because it is now stable. It approaches the asymptote. And therefore for number D, you're gonna get the roots that are complex only. So which is they're gonna be different. You're gonna get it here on the imaginary and then here on the imaginary. So this is margins. It's on the margins, ne? So, oh, by the way, here we're gonna say it is stable, and then again it is bounded. Okay, it is stable and it is bounded. Here when you have something that looks like this, right? It kind of looks like what we did at the beginning, but it's now on top of the margins. But the question is this stable or is this unstable? It is on margin. You see, it is stable because it almost ran away from the negative side, heading to positive side, but it just decided to stop here on the margins. You understand? So meaning it's gonna look like this, but it won't approach something. It will just fluctuate up and down, up and down, up and down within a specified range, within a constant range. So meaning here we're gonna have something that looks like this, and as a response, you understand? It's not going, it's not going like this. If it goes like this, you see, it is unstable because we can see that here it follows exponential decay just like this, even this side. So it won't be like this at all because the y values, we don't know they're gonna go up until when it's unstable. You understand? When it looks like this. But here it's like the okay, we'll do the compound decay later on. So here, these values over here are stagnant, are constant throughout, to show that it is not unstable, it is stable. So here, but we say it is marginally stable, okay? When it looks like this, it's marginally stable. And then again, it is bounded because it is stable. That's what matters. You understand? Yeah, that's how we answer these questions. So let me add again on the notes. If we have something like this, there are roots that looks like this, maybe it's this side and this side. So how is this going to look like? It is unstable, this one. But you have to understand it's going to be opposite. You see this side and this side, it is just like this to approach something. But when you have your roots on this side, it's going to be the opposite of this one. Let me show you how. It's going to be the opposite of it's going to start as if it is stable, and then it goes up. It is this basically. It is this thing that we see over here. It's the opposite of this. This one starts like it's crazy and it goes down and it approaches something. But this one starts as if like it's all doing well until it goes up. It fluctuates up and down, whereby it is now getting to be unstable. Okay, so that's how it actually works. So yeah, let's call it a day.